Magnusson, and I'm from ECMWF, European Centre for Medium Range Weather Forecast in Reading, UK. And this talk doesn't contain any final results. It's more of a discussion material, I hope, and will hopefully give you some insights of the problem we work on in both medium range weather forecast and seasonal forecast, and up to a longer time scale. So having a satellite image, and this is actually from yesterday, but it looks more or less the same every day when we look. We see different features that our model needs to handle. Along the equator, these white pixels are convective cells, which are very small scale, but also can be grouped into convective clusters that are large in scale. And going northwards, we have large areas with clear sky, which are areas with sinking air and high pressure systems. And when going more northwards, we have storm tracks with moving lows and highs and frontal systems. So these different features have different scales, and therefore one can expect different predictability for the different features. But then looking under what we have below the atmosphere is the ocean then, which is important at least for seasonal time scale and longer time scales. So on the back side of this photo we have the Pacific, where we have the El Niño circulation, and on even longer time scale we have the meridional overturning circulation, which we or some people at least believe could affect the climate for Northern Europe. But first mention a few details about the model we use. I will not give a comprehensive view. A similar figure was in Lenin's talk this morning, saying that we have difficulties with some of these processes. And I have to agree that clouds, for example, are not explicitly resolved in the model, but are more represented in a statistical way. So we have to have parameterizations for most of these processes, and the parameterizations includes the errors, of course, or simplifications, creating model errors. And in order to try to accounting for the problem Lenny mentioned about, for example, the ants in Southern America, we try to include subgrid orographic drag for unresolved processes along mountains. But that's also not a perfect model. So what we are dealing with is a highly imperfect model system. And the highest resolution we use today is 16 times 16 kilometers in horizontal and 91 vertical levels. And the time stepping are about minutes, soon down to seconds. So it's a quite computational demanding model. And for the data simulation we use a 4D VAR system. and the model is both working in the physical space, the grid point space, and using spherical harmonics, so the wave number space for some of the processes. And then for the longer time scales, the interaction between land and ocean is important. Of course, some of the land processes are important for really short time scale, or also albedo effects around snow cover. And having a snow cover, the ground and the atmosphere are isolated from each other, which can cause huge differences in the results, and potentially a large source for errors. So what's predictability? And this maybe a bit too simple for several of you, but one has to start somewhere. And discussing the average error, so not say from one single realization or one single grid point, but from many grid points and many realizations. We can estimate the time derivative, or the evaluation of the error, as some parameter times the error itself. So it will be an exponential increase of the forecast error with time. And looking at the data, we see that that's the case in the beginning, but we have to have an upper limit of the root mean square error in this case. The error cannot increase to an indefinite number, and that's limited by the climatology of the system.
What is the green line?
The green line is the root mean square error of ensemble mean in this case, for a monthly forecast. So, and in blue we have the error of the climatology, so the difference between the climate and the analysis. So one can see that as the most basic forecast you can make. You're just taking a climate map from the archive and saying this is the forecast. And for the ensemble mean, when the lead time increase, the ensemble mean goes to the climatology of the model, because scales are filtered out. So, and we see here about after 15 days, the error of the ensemble mean and the error of the climatologist are more or less the same.
So presumably the blue line isn't a random draw from the climatology, but it's actually the ensemble mean of the climatology. Otherwise, the blue line would be up with the red line.
No, the red line is the persistence. So if you take the weather today, you use that as the forecast for the coming month.
The persistence of any forecast over a long range.
Yeah.
So including a random draw, right?
Indeed, a random draw. Yeah.
So if the climatology was a random draw, as you said,
climatology is the mean. Is the mean.
The random draw would fall under red curve.
Yeah.
So is persistence generally worse than climatology because the small scales are still maintained and
yes.
persistent?
And that's an important property to know about looking at predictability predictability and RMSE error, because if we have the root mean square of one single deterministic forecast, it would asymptotically go up to this red curve, because one single realization includes all the small scale, which increase the possible variability around the analysis. So the difference between these two are square root of 2.
So why doesn't the green line go above the blue line?
Sorry? Why doesn't?
Why doesn't your finite ensemble get worse than climatology?
In this case, because we are close enough to an unbiased state.
That's
I think.
The long-term mean of an ensemble becomes the climatology.
Right. But
Yeah.
the finite time of the small ensemble will have more variation than the long-term.
But it is the mean of the small.
But having 50 members in this case,
And how many in your climatology?
don't know how many it is. It could be that this is the climatology of the ensemble.
No, then it's not so surprising.
No,
It's the climatology of the ensemble, not the climatology of the climate.
no. So in the case that we had a model bias, which for most of the variables we have, now I have chosen the geopotential height of 500 hectopascal of Europe, which is one of the easiest parameters to look at, because it behaves quite well in a dynamical point of view, and it has small biases. But if we had a biased system, the asymptotic value of the forecast error should be worse than the climatology. And in several problems, especially for the longer time range, it's quite hard to stay below the root mean square error of the climatology, and even the
What's the difference? I'm not sure. What's the climatology? Is it a simplified, different model that you do to do seasonal prediction or long-term prediction? What's the difference?
The difference is the time scale that we look at. So looking at longer time scale, the forecast value is so low, and model errors, model biases tends to show up more on a long time scale. So we can return to that problem.
I'm not sure what's in the climatology versus MOF-FC. You didn't say that to us, so we don't have the information. I don't know what's in the climatology versus what's on the MOF-FC model.
Okay, so the climatology is taking the mean of say all forecasts you have made, calculating the mean, not regarding any day, they are of course on the same season, but this is actually forecasts, so it's lead time dependent.
So like if you had an attractor, and you took
Not in some ways the blue curves are already at a high value.
the blue dots are sort of an estimate of the mean of the attractor, picking at random over the entire invariant measure and taking the average. Whereas the green dots are the average of an ensemble sorted on a particular day. So asymptotically, you hope they'll be the same.
Yeah. So
But this is true even for a perfect model. You could expect this in a perfect model.
yeah. So we can expect it in a perfect model, but not always in an imperfect model. So, but then is the question, for a long time do we have the predictability? Where do we set the limit of the predictability? Is it when we have reached the 90%, or is only 10% of the difference left between the value of the climatology and the value of the forecast? So that's an open question in predictability, how to define the limit of it.
Sorry, once again, what was the red curve?
The red curve is taking the weather for today and use that as a forecast. So that's the memory in the system, the persistence of a pattern.
It's basically a free trajectory. I want to say that.
I mean, you don't evolve it at all.
No.
You just use that map
Yes.
and you compare it 15 days
Okay.
later.
Yes. So also the world evolved, but not your forecast.
But do you really want to define predictability in terms of the RMS error?
No. That's the next question that I will
You
return
said it was
to.
undefined. I think it's not.
Yeah. No.
One remark can get this curve. Theoretically, the ratio of the ordinates of a red curve and the blue curve is a square root of 2.
Yeah. So now a figure, and it will be interesting to compare and discuss the results from the talk before, because I had actually prepared a similar figure, but from our model, calculating the error spectra. So the spectra of the difference between the analysis and the forecast for different forecast lengths and for several realizations. So the blue curve is the forecast error for 12 hours, 24 hours, 48 hours, 96 hours, and 192 hours.
This is again the ensemble mean.
This is a deterministic forecast in this.
Okay.
So it's not contaminated by any filtering process of scales. And here we have the wave number and amplitude of the error. And we see for the small scales, the error saturates almost immediately. So for wave numbers higher than 300, about, we have no skill even after 12 hours. But then looking at the larger and larger scales, we see that the predictability remains. But I think it looks quite similar as the figures we saw in the previous talk. That we lose, after this limit, then we lose step by step the predictability.
The different
Yeah.
times, yeah?
Yes,
Yes.
so it's different forecast lengths.
And what is the difference in time? In turnover times?
First is 12 hour,
Yes.
and so then it's doubles
Right.
for every dance, so
Right.
24, 48.
And what is actually the turnover time at the London polynomial 10, say? Do you have
So
the
sorry.
turnover time for that? The typical turnover time?
Roughly physically, what's the eddy turnover time for Legendre polynomial 10?
So 10
An idea?
means,
So 10 means sounds away.
10 means 40,000
3 days.
Yeah, about.
3 days?
So is this? It's on the synoptic scale, Bertinic wave scale. But it's hard to define the.
But what are actually the honest velocities in the atmosphere? They are like 100 meters per second or less than that? Almost like this, yeah?
Yeah, say 50, and this around 50 meters per second.
Yes. Okay.
But again, this could also be true in a perfect model.
Yes.
So, again, it's sort of hard to see how you could possibly get predictability out of this either.
Sorry, to get predictability out of.
A graph like this. This is showing
Yeah.
that if you make one run,
Yeah.
the errors tend to grow.
Yes. And if they go from small scale,
Right, yeah, that's
it's,
right.
so for long forecast is only the information in the longer scales.
For this initial condition.
Yes.
But there could be another initial condition where this stayed flat.
Yes. This is an average over a month of integrations.
Excuse me, to what do you compare this differences? I mean, what is
Yeah.
the truth that you try to?
The truth we don't know. Do you mean the saturation level?
Yes.
The saturation levels should be quite close to an 8-day forecast.
But the errors are evaluated with respect to the analysis, right?
Yes?
Okay, I know.
Yes.
Sorry, that's
Yeah,
yeah.
okay. Sorry.
Can you explain what happened at small scale? Why is there a range of scales where the error does not increase, and then at smaller scale, smaller scale it increases? Is it due to a particular feature? Can you comment on that?
So yeah, I mean, only think about what's happened down here a few days, but I think it has to do with the treatment of the end of the spectra, how the energy dissipates or not dissipates. Seeing that the error increase with time, could be that a model error develops during these days, so the model error increase. So having the slope of the spectra, we're losing more and more of the tail the longer the forecast goes.
This is the model running away from the initial condition.
Yes.
This is the model running away from the observation.
In the range of scales, around between number 400 and 600, the error does not increase,
No?
which seems to indicate that in the initial conditions, the error is already as large as its climatological value.
Yes?
Yes, so that's, in both scales, no information actually is introduced by the analysis. They
No.
seem to mean that, because the
Yes,
error is
yeah,
already
yeah,
as large
that's-
as it can be.
Yeah.
But then, how come that is this it can be smaller, the error can be smaller than it can become smaller than its climatological value, apparently, unless the bump at the very end is totally unrealistic.
No, I think at smaller scales, the analysis, the observations introduce structure that the model cannot support.
Yes,
So the model throws it away.
yes.
So at very short lead times,
The-
it looks good, but it's throwing that information. It can't support that information.
Does it have to do with the fact that the error is estimated against the analysis itself?
Yes.
That it is not estimated against totally independent observations, that it would be different? If the error was estimated against observations which are totally independent from the ones which have been used in the analysis, could the conclusion be different? At least
It could be different, but I don't think it's necessarily different. Because if we initialize a spectra like this, yes, but then as the time goes, we're losing more and more of the small scale. It will end up with an error. So even if at the 12-hour forecast all the scales are uncorrelated, we develop a model bias, so we will be even worse than uncorrelated.
so it's not an error, it's not due to the errors in the initial condition.
No, that's my interpretation of it.
But isn't the fourth bar is using lower resolution than the forecast model? The fourth bar has a loop with a model that has much lower resolution than this one.
But then the resolution of the loop is gradually increasing.
Yes, but it's never in the full resolution.
But even if it's full resolution, then you find a trajectory, but you needn't find a trajectory on the attractor of the model. So if the model relaxes onto a trajectory with different, an attractor with different spectral characteristics, it's modeler. You still see a bump. You could.
Yes. So then, moving on to longer forecast ranges we're interested in, I just put up a little reminder of how forecasts are used. And I don't know if all of you agree here, but if we produce a daily forecast, we run a forecast model for, say, 2 days ahead or 1 day. We're looking at more or less hourly output of the model. While if we're producing a weekly forecast, we're filtering out the hourly information, and we look at daily data. And then for monthly forecast, we're looking at weekly average. Seasonal forecast, monthly average. A yearly forecast, we look at the whole seasons, and decadal forecast that runs for 10 years. We average over years.
So Henry, just take the mean value of the forecasts.
Yes. Yeah, the mean value of the forecast range between, in this case for year 1, we're looking at year 1, year 2, year 3. And
so when you make your hurricane forecasts, do you average the wind speed over a month when you're making a seasonal forecast, or do you look at the hourly? Would you rather look at the hourly wind speeds and find the maxima over a month?
With a seasonal forecast, I presume it's just a count of minimum sea level pressures that are found. But there's no averaging that's done.
Yeah.
So it's essentially finding a frequency of occurrences.
I don't know any users who average like that. I only know med offices that average like that.
on the other hand, counting, then one had the counting period, which is in hurricane season, looking at seasonal forecast.
But counting within the month is very different from averaging over the month.
Yes, yes.
Right?
Yeah.
A farmer is interested in the hottest day or the driest day, not the average.
Yes. So I should change the word I use from averaging to the period where the information is collected, where the information is being together.
But the model time step is 15 minutes all the way out.
Yes.
So why does it make any sense to average ever?
Because the noise level of the data, so even if you have it could produce an hourly output or 45 minutes output, it doesn't make sense to look at every forecast day separately, but you look at a longer period.
So
but then is the question how you post-process the data inside that window.
Yeah, and it depends on the metric that you're interested in. So, like, seasonal forecasts would be worth averaging if one's just looking for sort of general signal, whether it would be, say, warmer than normal in the summer over Europe, say. But it wouldn't be looking at individual extreme events. So I think that's the philosophy behind doing this averaging.
But it means that you've already made a decision. I think more likely you've already made a decision you don't have much skill and therefore you average. But by doing that, you've already decided about predictability and you've taken the decision away from the decision maker and made it for, you know, if you decide the period to average over, then you've made lots of decisions.
So but then what I'm going to talk about the last minutes is going back to the slide where we discussed the upscale cascade of errors and the predictability limit about 2 weeks. And then we don't count to what's happened on the boundaries. So we can have boundaries in our system that have longer predictability. So for example, in the Earth system we have the ocean that have longer predictability, and then act as forcing on the boundaries that can add an extended predictability to the atmospheric system. And one also can see when working on climate models that the increase of greenhouse gases increases the predictability in the system. But then we need to have a predictability of how the humans behave with releasing the greenhouse gases.
The models are very good.
Yeah. If we have we can have a one-dimensional radiation model that we only increase the greenhouse gases and not getting the nonlinear effects, but only the radiation.
Just one last thing and I'll stop.
Yeah.
So the decadal forecasts, if you were looking at a decadal forecast and it was hotter, would you really want something over a year, or would you want to know whether it was hotter in August in the main development region versus hotter in January in the pole?
Yeah, again, it's a choice of the user, isn't it?
What? Not if you were looking only over time resolution of years. So.
But I don't understand why you don't do convergence as we do in fluid dynamics. I mean, you should run it with a month average, with a semester average, and then the year average. And if they all give the same answer, or almost the same answer, then you say, okay, I've converged my run. If they give completely out of work answer, then you say, let me think a little bit more about it. you know?
I think that's the sort of alternative that would very often would be nice to see that rather than see only the annual stuff.
Yeah. So, but an example, and this is a bit noisy plots and from decadal runs I made with our model. That's showing different sources of predictability, how they can show up. So this is now anomaly correlation coefficient, which I think is a better metric for predictability than the root mean square error. And the redder, the better, and the GU is neutral, then we don't have any predictability left. And if it's on the bluer side, the results are anti-correlated with the outcome, so it's even worse. So first here I have a month average over month 1, and this is based on 10 realizations, so it's not so many and 7 ensemble members. It's a limited data set. And for month 1, for the first year, we see that it's quite red everywhere. So this indicates that monthly forecasts are valuable over large areas. I have to say that this is for near surface temperature. Then looking at month 2 to 4, so the first season of the first year, we see that already at that point most of the predictability in the extratropics are lost. And it's mainly over the Pacific and the Indian Ocean.
There is nobody.
No.
No, but it's
And it's getting worse. It's getting worse. So this predictability is mainly from the El Niño, La Niña.
Variance.
Sorry? And then if looking at average over the whole second year, And it's not just little predictability left in the ENSO areas. But here some predictability starts to show up in the northeastern Atlantic.
The Gulf Stream or something?
Yes, I believe it's because the North Atlantic gyre. And if we look at manage to initialize the model correct, almost correct in this region of the year 2, this water have been advected further down in the gyre. And then looking at the average over year 3 to 5, you see that more red is popping up. And now we are moving in to the effect of the greenhouse gases. On this time scale, the temperature both in the model and in the atmosphere have slowly increased during these 50 years, where the model runs are based on. And that shows up as positive anomaly correlation.
They don't need to slowly increase. One can increase a factor of 10 bigger than the others.
Yes.
And because you're looking at a correlation and not actual an error, it will show up as being red.
Yes.
Yeah, I'm completely concerned. I don't see how by losing information you can regain it unless you are really something, as you say.
But that's because of here that the average period increases. So here's average over 1 month, here over 3 months, here over 12 months, and here over 3 years. So a lot of noise are
getting rid of.
Yeah.
Or could you also say that in the long run it's getting closer to the climatology, and therefore it's close to it?
No.
No, because when you're going close to climatology, you don't have any anomalies.
So I define climatology in the system you know is drifting.
Yeah.
Also, with the higher CO2, there are theories that mostly La Nina process instead of and that the climate gets more stable in the Pacific. I saw several papers about it, so that the climate should become simpler of the Earth.
Yes, in our model and in several other models, I think it will be really difficult to see, because the model tends to go in a more constant La Nina
Yes.
phase.
So that's.
But that's probably because of model errors. And it's hard to say if it's due to any physical reason it's going to.
But I think by Philander, so it's trying to explain physically why it should happen like that. And that in the past there were climates when it was a permanent La Nina.
Why doesn't like the dark blue for a user? You know?
Yes.
Yeah. The dark blue is as good as the dark red.
Yes. As for modeler, it's not so not good that the model is anti-correlated. On the other hand, if you apply a statistical post-processing, then you can dig out quite a lot of value from a.
Once you go to correlations, you've bought statistical post-processing already.
Yeah.
But yeah, so there's as much information in the dark blue as there is, but I agree, it's not physically pleasing.
No. On the other hand, for modeler, it can be spots start to looking at for model errors, and because there could be a potential of predictability there. So, shall I stop, or I have a few more slides?
Yeah, go ahead. You've already been asking questions.
Yeah. So, just to mention a little bit about some work I've been doing on systematic error strategies. And is related to Lenny's talk this morning. And having the attractor of the nature and having a model which the attractor is different from the attractor of the nature, we're facing a problem when running the model initialize, and we have to initialize the model. Because if we initialize the model close to the nature, the model will drift towards its model climate and then evolve. And what's happened during the drift is uncertain. For some processes, it can drift off the model climate and then slowly drifting back. And we can have it can kick some nonlinear processes during the model drift that will make the forecast even worse. So two strategies I have evaluated is first to try to initialize the model on its own attractor by, in my case, using a very simple scheme called anomaly initialization, where I add the observed anomalies to the model climate. And the other one is to use flux correction in the flux between from the atmosphere to the ocean in order to correcting for the model drift. And the model error we have, and this is from not the most recent model cycle that is in WF, but fairly recent, is a general cold bias. This blue color is 1 degree, this dark blue is around 2 degrees. So we have an enhanced bias in the tropical Pacific, where we have the ENSO. So the model after a few years are more or less in a constant La Nina stage and flipping with a low amplitude back and forth. But what the atmosphere sees is more or less a constant La Nina. So I try to apply a flux correction both in the momentum flux, so for the winds, and for the heat flux, and see what's happened.
So, I said general question first. So, your model is very nonlinear.
Yeah.
So, what does it mean? How this is, I realize this isn't your fault, but how could it possibly work to initialize a nonlinear model far from the physical variables?
Yeah.
For instance, if we look at the SST biases down near Antarctica, does ice not still melt at 0 degrees C?
Yes. In these model runs, we have a prescribed sea ice.
Oh, okay.
Yeah,
well,
but
I agree
I
that answers
understand
my
the point.
particular question, but the general question is if you've got a 2 or 3 degree bias in temperature,
Yes.
that changes the relative humidity, that changes the phase changes in ice.
Yes.
How could it be that? I agree you lose this question of things running away, but how could that help?
Help initializing here or here?
Yeah. How could, if you expect to simulate those feedbacks of ice or absolute humidity or such clouds, then if the model is that far away from reality, how can those feedbacks?
Yes, that would be my conclusion then.
Okay.
Yeah. in a minute. So if looking at El Nino forecasts, and this is the sea surface temperature average of an area in the mid-tropical Pacific. And in black we have the outcome, the analysis. So this is from this famous 97-98 El Nino. So starting from initializing the model from the analysis state, we see that during the first year, the model cools down and then stays on a level, and it's a few degrees colder than the observed. The first alternative is to use the anomaly initialization, where we initialize the model to 2-3 degrees colder than the observed. And we get an evolution of the model, and after 1-2 years, quite similar to the one we get from the control run. And the alternative with flux correction, we see completely different behavior. Not only the mean state is affected, but also the variability of the model. We see a much larger ensemble spread here, and some members covers what happened in 97, 98. So that's one of my main conclusions comparing these two strategies, that some errors are possible to account for in post-processing, but the feedback effects and the effects on the variability is very hard to account for then. And looking at or comparing these two for the precipitation over the tropical Pacific is quite large differences, because 2 degrees difference makes a large difference in the evaporation, and then the evolution of convective cells and so on.
How do you correct the wind? I mean, how do you change the wind and flux?
I add a seasonal dependent term in the flux sent from the atmospheric model to the ocean model. It's an additive.
So this takes care of your persistent line.
Yeah. So I think this relates to what was discussed about the initializing on the attractor, not the...
So somehow your flux corrections change the attractor, no?
Yes. And there's not only changing the attractor, but also the variability and the size of the attractor.
Yeah, but
So
changing
it's
the attractor
not
changes everything.
yeah. So it's two different models. One can see from looking at the El Nino simulations. Then for other parts of the systems, the effect is not so large. So that was what I had today.
Thank you. Other questions?
Another picture on it about hurricanes and these simulations. An example of nonlinear effects and compensating errors. Because we, in these simulations, have a constant La Nina, it seems to cancel the effect that we have a cooled SST in the tropical Atlantic. So the number of tropical storms in the Atlantic is actually more in this simulation with a cooled SST.
Well, with the La Nina, essentially it's cooler in the Pacific, but in the Atlantic it's independent, the SST. But what it does do is La Nina acts to regulate the vertical wind shear in the atmosphere and reduce the wind shear, and so that then provides enhanced tropical cyclone activity in the Atlantic basin.
Yeah.
So if you keep running the lower graph,
Yeah.
what happens next? I ask because it looks like in 97 you've got 2 El Nino members and about 5 non-El Niños, and in the 98 you've got 2 different El Nino members and 5 not. You always get 2 El Nino. That would give you about 1 every 3 or 4 years in a single run.
Every 3 years, the frequency is a little bit too high in these runs, and the amplitude is somewhat too large.
But it looks pretty good compared to.
It looks much better than this one. So this indicates back where we should look in the atmospheric model for systematic errors. And the largest contribution for this one is actually from the momentum flux. So we have a wind bias in the tropical Pacific that enhance the water circulation and then gives a positive feedback.
Okay. Any other questions? So, thank you again. Any instructions?
Not really. So back to work, everybody, of course. And then let's do that. And then tomorrow we have the talk by Sharon at 1:30. That will be in here.
1:30.
1:30, yeah.
And nothing tomorrow morning?
Good.
You got any lecture tomorrow morning? No. And we don't have time to work.
Maybe you should say it first. You'll be sitting there in a place where there's no.
About the exercises, Gustavo can say a few words about the axis. You set it up, yeah?
Yeah.
Did you make the implementation?
Alors, il y a quoi de
You can argue.